Alright, so we're going to try something new here. I'm going to record on my iPad, so hopefully this records well and is helpful, but we'll see. It may be a one-time thing, but let's look. So we're going to look at analyzing some graphs, so finding things like domain, range, increasing, decreasing, maximums and minimums of different functions. And we'll start, of course, with number one. Number one, given the function f of x equals x squared plus 3x plus 2, we're asked to find all of the information a through e. Now, a lot of that information would be relatively easy to find if we knew what the graph of this function looks like. In some cases, I'll give you the graph and ask you to find a through e. In other cases, I'll just give you the function, in which case you have to graph it first, and then go back and look at the, see if you can find that information. So, given a function like the function here in number one, if I am trying to find the domain and range of this function, then how are we going to do that? There are several ways to find domain and range of different functions, but when I look at this function, I see this x squared right off the bat, so I know that this is a quadratic. And if I can, over here, maybe just remind myself what a quadratic looks like, it's that U shape. I've made a little bit of an assumption here, drawing it pointing up or opening up, but I hope you can justify on your own that this is indeed going to be the case. This is a parabola that opens up, and hopefully you remember the reason why is because the number in front of x squared is a positive number. Although it doesn't look like it, there's a positive 1 kind of implied to be being multiplied in front of that. So we have this quadratic in shape, and so automatically, because this is a quadratic, it doesn't matter where on the graph it is, its domain is all real numbers. Going left to right, the function is infinitely wide. It has a domain of all real numbers. If you wanted to write negative infinity to infinity, I would accept that. Either one is okay here. So all real numbers or negative infinity to infinity. Almost always, if the domain or range is negative infinity to infinity, I would write this just so it saves some time. But what about the range of this function? What's the range of this function? Well, for that's going to be pretty difficult to tell just by looking at the equation. We know that the range of a function is basically from lowest to highest, what are the y values? So the low point would be here, and then the high point would be up to positive infinity. So the range here is from whatever this low point is to infinity. We're going to have to take some time later to figure out what that low point is. So for now, we may leave that as kind of a question mark. What is this low point here? That we don't know, but we can find it later. For now, let's move on to the zeros of this function. So let's see if we can't find the zeros here. Now the zeros of a function visually are the x-intercepts. But how do you find it if you can't visualize it? Like we don't have the graph to look at here, so we're not quite sure where it crosses the x-axis just yet. There is a way to find this, and the way to find x-intercepts every single time is to set the function equal to 0 and solve the equation. Set the function equal to 0 and solve the equation. How do you solve this equation? Well, this is a quadratic equation. There's that x squared. So when we're solving quadratic equations, the best way, arguably the only way, to solve this is to factor it. So to figure out what multiplies and adds to certain numbers. Hopefully you remember factoring as what multiplies to the last number while simultaneously adding to the middle number. The only way that I can think to multiply to 2 is 2 times 1, and indeed, not only is 2 times 1 2, but 2 plus 1 is 3, so it looks like this will factor into x plus 2, x plus 1. Nice. Okay, this is factored, but it's not solved. So a lot of you probably remember how to do this, but I'll go through it in detail. If you have a factored quadratic, so x plus 2 times x plus 1, what we are saying here is that x plus 2 times x plus 1 is equal to 0. Well, if we think for a second, we'll remember that the only way that it's possible for two numbers, x plus 2 and x plus 1, to multiply to get to 0 is if one of them is 0. The only way that something times something is 0 is if one of them is 0. So we're going to set each factor equal to 0 and solve the resulting equations. Okay. If x plus 2 is 0, then 0 times x plus 1 is 0. Or if x plus 1 is 0, then 0 times x plus 2 is 0. So if it's the case that x plus 2 is equal to 0, then by subtracting 2 we get x equals -2. And if x plus 1 is 0, by subtracting 1 we get x equals -1. So these are the two zeros of our function. X equals -2 and -1. Let's find those on the graph. So -2 and -1. Here's -2. Here's -1. These are our zeros. Cool. Another piece of information that isn't explicitly asked for here is the y-intercept. What's the y-intercept of this function? So maybe we have another part up here, maybe part f, be the y-intercept. What's the y-intercept of this function? Well, if to find x-intercepts, or zeros, you plug in a 0 for y, then to find y-intercepts, you plug in a 0 for x. So let's do that. Let's look at our original function there and plug in a 0 for every x and see what we would get. Y, or f of x, equals 0 squared plus 3 times 0 plus 2. Hopefully it wouldn't take you very long to realize that when x is 0, y is 2. When x is 0, y is 2. So it looks like the y-intercept is the point 0, 2. Cool. So there's quite a bit of good information here, and we're very close to being able to get a good graph of this thing. The only thing we don't know is the maximum and minimum values. Right off the bat, if I were to imagine this shape that we've already talked about, certainly it's going to have a minimum value. We've been hunting for that for a while. But notice it will never have a maximum value. It just goes up and up and up forever, off into infinity. There is never, quote unquote, a tallest point. It just keeps going and going forever. So there actually is no maximum. So we're not actually worried about that. But we are worried about the minimum. How would you find the minimum? You find this minimum. And it's actually going to be kind of tough, but let's think. If this is -2 and this is -1, and we know the graph goes through this point. No, I don't want a straight line. We know the graph goes through this point and the y-intercept, and because it's a quadratic, it's opening up like this, so we can at the very least imagine this shape. So then somewhere down here is that minimum value. And the question would be, well, how do you find it? And maybe a lot of you are saying, well, what if you just found the halfway point between -1 and -2, maybe -1.5, and said, okay, when x is negative 1.5, then y is what? That's going to be our strategy here. We know it crosses the x-axis at negative 2 and negative 1. So if we found that halfway point of negative 1.5, we can plug this in for x into our equation, and it will spit out a y value that we can then plot. So let's go back through that process and see if we can't figure out where on earth that minimum value is. So maybe over here. We said that we were going to plug in x equals negative 1.5 into our original equation. What was that again? Oh yeah, x squared plus 3x plus 2. So y equals x squared plus 3x plus 2. But I said I was going to plug in negative 1.5 in for x. So y equals negative 1.5 squared plus 3 times negative 1.5 plus 2. I'm going to use a little bit of a trick. Almost always when you're evaluating stuff like this, working with decimals, at least for me, is a little tricky. So I'm going to use this same number but as a fraction. Realize 3 over 2, 3 divided by 2 is 1.5. So instead of negative 1.5, I'm going to call it negative 3 over 2. Just because, as we're going to see, it's a lot easier to multiply and to square fractions than it is to multiply and square decimals. But if you're comfortable using decimals, then by all means, go for it. So what's this going to equal? Well, the first thing we have to contend with is what on earth is negative 3/2 squared? Certainly when you square a negative number, this is going to be positive, so that's nice. But how do you take a fraction and square it? What is 3 over 2 squared? And the answer is 9 over 4. So try and imagine how I got that. And maybe it wouldn't take you all that long to realize, oh, it looks like he just squared the 3, which I did, and squared the 2, which I did. So 3 squared is how I got the 9, 2 squared is how I got the 4. Why was it positive? Because a negative squared is always positive. Okay. What about this thing here? What is 3 times negative 3 over 2? Well, if we think of 3 as a fraction by putting it over 1, then 3 over 1 times negative 3 over 2 is actually going to be negative 9 over 2, right? Top times top, bottom times bottom. 1 times 2 is how I got the 2 on the bottom. 3 times negative 3 is how I got the minus 9 on top. And then let's not forget plus 2. Okay, I'm going to make everything a fraction here. So 9 over 4, 9 over 2, 2 over 1. 9 over 4 minus 18 over 4 plus 8 over 4. What on earth did I just do there? Well, I realized that there was a 4 on the bottom, a 2 on the bottom, and a 1 on the bottom. So I took this 4, 2, and 1 and made everything a common denominator. So it looks like I multiplied this whole fraction by 2 to get a 4 and an 18, and it looks like I multiplied this whole fraction by 4 to get an 8 and a 4. Okay, and as long as I do that multiplication on top and bottom, we'll be okay there. All right, and then now the rest is easy. 9 over 4 minus 18 over 4 plus 8 over 4. 9 fourths minus 18 fourths is negative 9 fourths, because 9 minus 18 is negative 9, and you keep the denominator. 9 fourths minus 18 fourths is negative 9 fourths, plus 8 fourths. Negative 9 fourths plus 8 fourths is negative 1 fourth. Whew! Quite a bit of work there to find that maximum, or in this case, minimum value. But we did it, right? All of this work was finding that minimum value. So remember, when x was negative 1.5, we just did all that work to realize that y is negative 1/4. So when x is negative 1.5, y is negative 1/4. And there we have it, folks. Now we have for sure enough information to graph this thing. Oh, why did it go away? Awesome, and there's our quadratic. Okay, let's see if we can't come up with the increasing, decreasing, and constant intervals, and is it concave up or concave down, those intervals. Let's do the easy one first. Let's do intervals of concavity. So the first thing we got to answer, if we're going to answer part E, is it concave up or concave down? And remember, concave up is a U shape, concave down is the opposite. So this shape is concave up, this shape is concave down. If it looks like a U, it's concave up. If it looks like an upside down U, it's concave down. Okay, so it goes kind of, I think it's pretty obvious that this is concave up, and it's always concave up. Some graphs are concave up, and then they change to concave down, and then they change to concave up, right? This graph is only ever concave up. So it is concave up everywhere for all real numbers. From negative infinity to positive infinity on the x-axis, it is always concave up. Okay. Remember, the term interval, this is a crucial idea, is focused on the x-axis. Okay, so it was concave up from negative infinity to positive infinity. From left to right, it's always concave up. Okay. Cool. All right, so then let's look at the last part of this, which is increasing, decreasing, and constant intervals. Increasing, decreasing, and constant intervals. Maybe increasing we'll do in this lime green. Decreasing we may do in gray. Whoa, edgy. And then constant we'll do in brown. Blank. Okay. But there's no point in really talking about constant intervals here because this graph is never constant. When I say constant, I mean perfectly flat. This graph is never perfectly flat. It's either rising or falling. So these constant intervals are of no use to us. But it is increasing and decreasing. Okay? And remember, the term interval has been used here. So this is a consideration of the x-axis. So basically what this question is asking is, where on the x-axis is the function rising, and where on the x-axis is the function falling? Nowhere is the function constant. So let's look at the increasing intervals. At least visually, I hope you agree that from here, from here and beyond, all of this is a section of the graph that is increasing. But it is increasing from, it is increasing from, on the x-axis, from here and beyond. Okay? Yes, I understand that the function has a low point at negative 1/4 and then just continues to rise forever. But that's not what the word interval is asking. It wants to know over what section of the x-axis is the function increasing. And it starts its increasing process here, and it continues to increase no matter how far along the x-axis you go. Okay? So it is increasing. It is increasing from where to where? It looks like it started increasing at negative 1.5 on the x-axis, and it never stopped increasing, so to infinity. Luckily for us, when we're talking about increasing and decreasing intervals, we get to use parentheses every time. We don't have to really worry about closed or open brackets when we talk about increasing, decreasing, or constant intervals. That's nice. All right, so then what's next? Where is it decreasing? So we did that in gray. And it's decreasing, well, certainly if you look, again, I know that you probably remember this, but some detail for those of us who are a little rusty. If you look at it, it's definitely falling over this whole section. Okay? But the most common mistake I see is somebody saying, oh, it's falling from positive infinity until negative 1/4. But that's looking at up and down, that's looking at the y-axis. When we talk about increasing and decreasing intervals, I want to know over what section of the x-axis is it falling. And it's falling, well, it begins falling way out there at negative infinity, and it doesn't ever stop falling until here at negative 1.5. Okay, so this graph is decreasing from negative infinity to negative 1.5. Over that interval, it is decreasing. Okay. Looky there, man. Nice. So that's the full analysis on this function. Probably in class, we'll look at square root x squared minus 4 and talk about what that graph is going to look like. Okay. In the next video, I'm going to look at 3 through 9 and see if we can't ultimately finish the rest of this worksheet.